Hello everyone. This is for the first section, the introduction to limits for pre-calculus. The example I've chosen to start off with you guys is how far you can see from a given height. So this side is your height, and this is the curvature distance here. I'm hoping that it's totally intuitive for you that the higher you are, the farther you can see. You know, if you walked outside here, how far away is the horizon? Whereas if you drove out to Blue Mountain State Park and you climbed one of the towers, which I'm hoping most of you have done at some point, you can see further because you're higher. Or you've flown in an airplane, you can see further because you're higher. The higher you go, the farther you can see. So the question I have for you is, what is the limit to how far you can see? Is there a maximum distance you could see? If you were to go 1,000 miles up, how far could you see? If you were to go 10,000 miles up, how far could you see on the surface of the Earth? Or 1,000,000 miles? Whoops, 1 times 10 to the 6, that's what I was trying for. If you were to go 1,000,000 miles up, how far could you see? Does that number continue to grow, the curvature distance, or does it stop at some point? What I'm hoping, before we even do the math that's behind it, is that I'm hoping that you can start to see that the higher you go, you're only going to see so far on the Earth. And that being, you're only going to see up to this point. You're not going to be able to see around the corner. The highest you could go would be infinitely high. If you were to go a gazillion miles out, or however many digits that is, really big. This distance is only going to grow to this point. It can't grow past it because you can't see around the corner. Okay? There's a maximum distance of how far you can see. So there's a limit to how far you can see. So let's figure that out. If you were to draw these across, all right? This I'm hoping that you see is a right angle, so that's 1/4 the circumference of the Earth. Well, how do you find circumference? That would be 2 pi r. So this would reduce, so you'd have pi r over 2. Okay, well, let's try it mathematically. This is a formula for finding how far you can see from a given height above the Earth. Filled in radius of 3,960 miles, 3,960. And what you're trying to find then is, what is the limit, and that's what you call this. You call this the limit as h goes to infinity, as your height goes infinitely far up. What is the number that this becomes worth? So as this becomes infinity, as you get bigger and bigger and bigger and bigger and bigger, what is that value worth? Well, let's try it. Okay, where's the pen back again? If I fill in infinity, I've got 3,960 times inverse cosine of 3,960 over 3,960 plus infinity. Wouldn't 3,960 plus infinity really just be infinity? I'm just trying to talk to you guys through this. You got this over something really big. 3,960 plus infinity is something really big. What is this fraction worth? It's working on you guys' number sense. Let's call it 4,000. Let's just, so we can work with easier numbers. 4,000. If I divide by 10, I get 400. If I divide, by 100, I get 40. If I divide by 1,000, I get 4. So the bigger and bigger and bigger I divide by, the smaller and smaller number I get. So it was 400, this was 40, this is 4. I'm hoping that you know in your heart of hearts, something divided by huge is going to be worth 0. Okay, so take it a step further. 3,960 times the inverse cosine of something that's worth 0. Now, trying to remember back to doing trig, that's asking where is your x value 0? It's 0 here, and it's 0 here. Okay? This is the one that we're going to be interested in, the very first one we come to. What is that angle where your x value is 0? Okay, it's 0 at pi over 2. So this is worth pi over 2. 3960 times pi over 2. Now, look at this. What is r? 3960 times pi over 2. They match. The farthest you could see would be 3960 times pi over 2. Now this reduces, I think that's 1780, I think. Let me check that on the calculator. See if my memory's right. 3960 divided by 2. 1980. Okay, I was close. Alright, we can fix that, hurry. 1980 pi. It's the farthest you could see. That is the maximum distance you could see on the surface of the Earth. Alright? Try this one. End behavior. We've talked about end behavior. Say you had a cubic function. As you go really far left, you go really far down. As you go really far right, you go really far up. Well, what about an even function, or sorry, an even degree function, say x squared? So this one was cubic. As you go really far left, you go up to infinity. Really far right, you go up to infinity. You guys are really doing limits. So let's take this one. What is the limit as x goes to negative infinity of x cubed? Well, this says as x goes really far right, sorry, really far left, I'm directionally impaired right now, your y value goes really far down. So the well, it's okay, it's not an answer. We have to talk about limits at infinity. A limit, if you're going to have a limit, you have to get a number like 5 or -7 or 201. As you go really far left, you're going really far down. So initially you're going to say it's going to negative infinity, but it's not a concrete number. So there is no limit. There is no limit. The limit does not exist. Okay? Because to be a limit, you have to get a concrete number, like back here. A quarter of the way around the Earth. That's a concrete number. Okay? So let's try this one. I'm just trying to introduce the idea of end behavior. All right. As you go really far right, is what that says. The limit as x goes to infinity. What is the graph doing? So as you go really far right, I'm hoping that you're starting to see that this graph is leveling out. Well, let's look at the table. I told the table to start at 0 and count by 10. So, in other words, I told it to start at 0, so I get 5 over 0 minus 2 plus 7, so that's -5 halves plus 7, so that's -2 1/2 plus 7 is 4 1/2. So that's where that 4 1/2 comes from. Then I told it to stick in 10. And then I told it to stick in 20 and 30 and so on. That's what I did here. And look at the y values. See how the y values are decreasing? Okay, let's see if they plateau. Let's see if they level out. So I went back and told it to start at 0 and count by 100. So the same 4 1/2 because I started at 0. And it's picking up where this one left off. Okay? And look, they continually are getting smaller. So then I said, okay, how about count by 1,000? 1,000, 2,000, 3,000. Notice again, it picked up where it left off. Again, they continue to get smaller and smaller and smaller. I told it to start at 10,000 and count by 10,000s. And so on until, look, the calculator, you've reached the accuracy of the calculator. It's telling you 7. Well, look at this. Okay, let's go back and look at why it's doing that. It's exactly the same as in the last problem, is that you've got a fraction and something's being left. 5 over infinity minus 2. Well, if you had infinity, would you really notice if you cut 2 away, if you took 2 off it? Nah, you'd pretty much still be at infinity. Plus 7. 5 over ginormously huge. What is that worth? Just like in the last problem, it's worth 0. So 0. Oops, why did I say 0? Oh my goodness. Whew. Somebody's not paying attention. Okay, 0 plus 7 is 7. And that's saying that there's a horizontal asymptote at 7 at y is equal to 7. You found its end behavior by looking to positive infinity. Okay, so there you go. That's another example of a limit. Now, what we're going to start doing is looking at limits at actual numbers rather than, say, at infinity. So we're going to start looking at, say, take the limit as x goes to 3. Okay, so here it goes. All right, still going to stick with the idea of doing it graphically. All right, as x, so I've phrased it before, I'm going to say it again. In order to have a limit, you need to get a concrete number like 2/3 or 5 or -5 or -7 or 12. You need to have an actual number. As you go really far left, that's what that says, you're anticipating this graph is going to continue to go down. It's going to go down. So its end behavior is going to be negative infinity. But it's not a concrete number. So there's no limit. It does not exist. Hammer time, whatever you guys want to call it. There isn't a limit because there isn't a concrete number. Okay, let's look at x value of -2. Notice there's a hole in the graph. Initially you might say, well, the graph doesn't exist because there's a hole there. Here comes the idea of when you're taking a limit at a number, the limit has to exist from both sides, unless you're looking at infinity. Now, let me back up and look at this. So as you come at -2 from the left side and from the right side, as you come at it from the left, your y values are coming up, and your x values are coming, your y values are going down, 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 down. As you approach from the left and from the right with your x values, the y values here are decreasing, the y values there are increasing, until you get to this point. At that exact point, the graph doesn't exist. There's a hole there. But you can get infinitely close to that point, can't you? Yes. What is the y value from both sides approaching as you do that? It's 0. Your limit actually exists. It's not a hole. It's not hammer time. It's not there isn't one. It's approaching 0 from both sides. Okay. This idea is new, so I understand if it's giving you some grief. I'm not trying to dismiss it. If you're confused, let's just move on and see if we can smooth it out. As you approach -1. So as your x's approach from both sides, as your x's get closer from this direction and as your x's get closer from that direction. Alright, you guys, sorry about that. The custodian wanted to come in and change the garbage. Take out. How about that? You don't want to change out the garbage. Okay. So as I was saying, as you're approaching -1 from both sides, as you approach from the left side, your y values are increasing. As you approach from the right side, your y values are increasing. Well, at -1, doesn't it look like it's taking on the value right here? So what would that y value be? So let's go 1, 2, 3, 4, 5, 6. What do you think? A limit of 6? Okay, works for me. At 1, here's another hole. As you approach 1 from the left side, your y values are decreasing up to that point. As you approach it from this side, your y values are increasing over to this point. Well, what point does that look like it is? I'm anticipated it to be a whole number. I'm not trying to trick you or anything here. 1, 2, 3, 4. So it looks like to me -4. All right. As x approaches 2. Well, how about -6? And as x goes to infinity, does it level out or become an actual concrete number? No, it continues to go higher, so it's going to infinity. So to me, there is no limit. The limit does not exist. There's none. Hammer time, HT, whatever you want to call it. All right? So let's go to -infinity. Well, it looks like as you go really far left, Your graph is continuing to go down, 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 down. So it's going to negative infinity. So there's no limit at negative infinity. And negative 6, 1, 2, 3, 4, 5, 6. So right here, come down. So what do you think? Negative 3. At negative 4. Right here, that looks like a high point. So what do you think? Negative 2. Okay, at negative 3. Well, to me it looks like there's a vertical asymptote right here. So as you approach from the left, as you approach that asymptote from this side, your graph is going down to negative infinity. As you approach the graph from this side, your graph is shooting up, so it's going to positive infinity. It is not converging to the same number. Even if you had a graph that was doing this and doing this, at let's say this value right here is the negative 3. This side would converge or go to positive infinity. This side would go to positive infinity. They're both going to the same place, positive infinity, but once again, I can't give infinity as an answer. It's not a limit. A limit has to be a concrete number. So once again, the limit does not exist. Okay, so as you approach 0, what do you think? 1, 2, 3, 4. As you approach positive infinity, again, it's going to diverge. It's going to go away. And that word I just used was diverge. It's divergent. It goes away from, not converging, which means it would come together. Okay. So as you go to negative infinity, you're going to negative infinity, so there's no limit. At negative 1, okay, this is a good question. At negative 1, one value is here and one value is there. So as you approach negative 1 from the left, it looks like you get 1, 2, 3, 4. So it looks like you're getting negative 4. As you approach negative 1 from the right side, as you come at it from the right, it looks like you're getting about 3. Are they converging to the same number? No, they're not. So there's also no limit for this one. This is an example where I'm hoping you start to understand the seeing the limit from both sides. Okay, as you come at it from negative 2. Negative 2? Oh, it looks like 0. I don't know why. I've been doing all these kind of linearly. I don't know why I have those two switched. I should really switch those two. Okay. It doesn't have to be. I'm just talking aloud. Okay, as you approach 0, it looks like you get 3. Well, how could that be? Well, I don't know. How about that one's supposed to be 2.5 then? But the idea is, or maybe this is 3.5. How about that? I make that better. How about that? Make it look a little. Then it doesn't match well what I said was going on at negative 1. All right. 2. At 2, what do you think? 4? And as you go off to infinity, the graph is continuing to grow, so there wouldn't be a limit there. Okay, here's a step function. It doesn't matter which ends are which. Like sometimes it's open, that's closed, or if this is closed and this is open, it's not going to affect our answers. So here goes. As you go to negative infinity, I guess I'm assuming these steps are the steps are continuing, so there wouldn't be a limit. As you go to negative 6, 1, 2, 3, 4, 5, 6. What's the y value? You were right about there. So 1, 2, 3, 4, 5, 6. Looks like negative 6. At negative 4, 1, 2, 3, 4. As you approach from the left, you're negative 6. As you approach from the right, you're at 2. They're not the same number. Doesn't matter what the circle is at either end. It makes no difference at all. You're approaching 2 from this side, you're approaching negative 6 from that side. So there is no limit at negative 4. At negative 2, you're at 2. At 0, you're at 2. At 3, here you're at 2, there you're at 1, 2, 3, 4, 5, 6, 7. It doesn't matter what type of circle is at which end. There's no limit at 3. At 6, you're going to be at 7. I'm assuming these steps are going to continue. I have no information to tell me they don't, so there isn't a limit. All right, let's go to the next page. Look at this one. What is your limit as you go to negative 5? So at negative 5, you're right there. As you approach from this side, and as you approach from this side with your x values, your y values are getting closer and closer to 2 from below, and 2 from above. So your limit would be 2. At -4, there's no limit, because here it's 3, there it's 4. As you approach from this side, you get 4. As you approach from this side, you get 3. There's no limit. At -3, you're at 4. At -1, same thing. Here your limit from the left side is 4. From the right side is going to be 2. There's no limit. As you approach 1, from both sides, even though there's a hole here in the graph's value, that if this was some function, and I said give me, f of 1, it would return an answer of 2. The limit as you approach from the left side is getting closer and closer to 0, and the limit as you approach from the right is getting closer and closer to 0. The limit as you approach 1 from both sides is 0, not 2. Sometimes this is a real hard one for kids to wrap the head around. Even though at that point the coordinate 1, 2 exists, it's right there. At 1 it's worth 2. That's not what this says. Sometimes you're allowed to just fill the number into the equation. Other times you're not. The limit has to exist from both sides. It has to be the same number, which is 0, not 2. Okay. At 3, so 1, 2, 3, as you approach from this side, you get 2. As you approach from the right side, you're getting -2. There is no limit at 3. At 5, looks like, how about let's just call it 3. At 6, looks like we're at 5. And as you go to 8, there would be no limit, 5, 6, 7, 8, because the limit has to exist from both sides. As you come at it from this way, you get 1, but there's no graph over here to come at it from, so there's no limit. The limit has to exist from both sides. Okay, I think that's the intro to limits. Let me go one more page, take a look. Yep, so that ends day 1. Your homework tonight is reading about the Zeno paradox. It was Zeno paradox, and reading about Thomson's, or trying to solve the problem on Thomson's lamp. Okay, thanks